To increase the efficiency of the gas turbine engine, the air being fed into it must be compressed before it has fuel added to it, and it's burnt in the combustion chambers, and it's subsequently expanded in the turbines. There are two types of compressor being used in engines presently available. One allows axial airflow through the engine, while the other creates centrifugal flow through the engine. In each case, the compressors are driven by a turbine, which is coupled to the compressor by a shaft. The centrifugal compressor is much more robust than the axial flow compressor. That, and the fact that it is the easiest and cheapest of the two types to manufacture, made it the compressor of choice in early gas turbine engines. The centrifugal compressor does, however, have one or two disadvantages, which have relegated it to the second position with regards to its use in large modern engines. Firstly, if we compare two compressors, one centrifugal and the other axial, each having the same frontal cross-sectional area, we would, first of all, find that the axial flow compressor can take in a far greater mass of air than the centrifugal compressor, and secondly, that much higher compression ratios can be attained in the axial flow compressor. Since the amount of thrust generated by a gas turbine engine depends partly upon the mass of air flowing through it, it can be demonstrated that when comparing two engines, each having the same frontal cross-sectional area, the engine which has an axial flow compressor will generate more thrust than the engine with a centrifugal flow compressor. We'll now examine the principles of the centrifugal compressor. The turbine assembly, attached to the compressor by a shaft, converts the pressure, velocity, and heat of the gases passing through the turbine into mechanical energy, which is used to drive the impeller of the compressor round at high speed. Air is introduced continuously into the eye, the center of the impeller, by rotating guide vanes, and centrifugal force causes the air to flow outwards, across the impeller, towards the tip. Because of the divergent shape formed between the impeller blades, the pressure of the air increases as it flows outwards between them. And, because the turbine is adding mechanical energy into the equation, the air's velocity also increases. The air leaves the tip of the impeller and passes into the diffuser section. The diffuser section is a system of stationary divergent ducts. The ducts are designed to convert the kinetic energy of the airstream, its velocity, into potential energy, pressure. As you can see from the graph, in practice approximately 50% of the pressure rise across the compressor occurs in the impeller, and the other 50% in the diffuser section. The compression ratio of a very efficient single-stage centrifugal compressor would be in the region of 4:1. This means that the outlet pressure of the compressor would be 4 times greater than its inlet pressure. To attain greater engine compression ratios using centrifugal compressors, 2 of them would have to be used in series with each other. In practice, it's not been found feasible to use more than 2 centrifugal compressor stages together. Excessive impeller tip speeds and extreme centrifugal loading prohibit efficient operation of a 3rd stage. As a result of this, engine compression ratios of much greater than 12:1 are not considered possible using centrifugal compressors. We'll now examine the principles of the axial flow compressor, which are basically the same as those of the centrifugal flow compressor. The axial flow compressor converts the velocity of the airstream, its kinetic energy, into potential energy or pressure. The means which it uses to achieve this conversion are, however, different to those used in the centrifugal compressor. The axial flow compressor, an example of which is shown here, consists of a number of stages. A stage embodies one row of rotor blades of airfoil section which are fastened to a disc, followed by one row of stator vanes also of airfoil section. The stator vanes are fastened to the compressor outer casing. The spaces between the rotor blades and the stator vanes form divergent passages. A number of discs, the number equates to the number of stages, are fastened together to form an integral rotor drum, which is driven by a turbine. In the rotor blades, which are turned continuously at high speed by the turbine, mechanical energy is added and converted into both kinetic, velocity energy, and potential, pressure energy. Within the stator vanes, the air pressure is increased by the conversion of the kinetic energy into pressure energy. Essentially, then, the rotor stages of an axial flow compressor can be seen as doing the same job as the impeller in a centrifugal compressor, while the stator stages of an axial flow compressor can be compared to the diffuser in a centrifugal compressor. The pressure rise across each stage is only quite small, the ratio being about 1.1 or 1.2 to 1. This means that in the first stage, the pressure might only increase by about 3 pounds per square inch. As a consequence of this, in order to achieve the compression ratios demanded by more powerful engines, many rotor stages may be fitted on one shaft, which is driven by its own turbine, as shown here. Assuming that the pressure ratio for each of these 10 stages was 1.2 to 1, the output pressure for this compressor would be in the region of 91 pounds per square inch. This arrangement, where a number of compressor rotor stages on a single shaft are driven by a turbine, is termed a spool. In larger, more modern engines, compressors may consist of up to 3 spools. So effective is this method of compression that in an engine like the Rolls-Royce Trent, compression ratios in excess of 35 to 1 can be attained. In this engine, the pressure rise over the last stage may be greater than 80 pounds per square inch. The high pressures generated can result in compressor outlet temperatures of up to 600 degrees Celsius. Although we have only shown engines which have just centrifugal or axial flow compressors, some lower-powered engines do use a combination of centrifugal and axial compressors. The space between the rotor drum and the compressor outer casing is called the air annulus. To maintain the axial velocity of the air reasonably constant as it passes through the compressor, as it's being compressed into a smaller and smaller volume and its density is being increased, the size of the air annulus must be reduced. This gradual convergence of the annulus is achieved by either tapering the compressor outer casing or the rotor drum, or, in some cases, a combination of both is used. Increasing the compression ratio of a compressor makes it progressively more and more difficult to ensure that it operates efficiently over the whole of its speed range. This diagram shows the vectorial relationship between the axial velocity of the air flowing through a compressor and the RPM of that compressor. That relationship gives us the angle of attack over the rotor blade and determines the pressure zones either side of the blade. If the compression ratio of this particular compressor is designed to be 22 to 1 at 100% engine RPM, then this diagram depicts the volume of a unit of air under normal compression reducing as it passes through the compressor at 100% power. The vectorial relationship between the engine RPM and the airflow axial velocity will give this angle of attack over the rotor blade, and these pressure zones, which are the optimum that would occur at the design point. The design point is that point in the engine's performance criteria where it's operating at its optimum compression ratio, RPM, and air mass flow. The problem which is associated with the compressor operating efficiently over its complete speed range is caused by the fact that the compression ratio of the engine falls as the speed of rotation of the compressor falls, and vice versa. Therefore, when the engine is operating at low rotational speeds, the air is not being compressed so much as at the design point, and the volume which it occupies inside the engine becomes greater and greater. Here the engine has been throttled to 60% of its full power setting, and the compression ratio has now reduced to 11:1. The volume of the same unit of air entering the compressor is larger when compressed only by 11:1 than when it was compressed at 22:1. To get through the compressor in the same amount of time it took when it was compressed at 22:1, the increased volume of air must be moving faster. The changed relationship between the increased airflow axial velocity and the reduced RPM will give a low angle of attack over the rotor blade, which will reduce the size of the pressure zones as shown here. If, on the other hand, the engine is allowed to rotate faster than its design maximum, then its compression ratio will increase accordingly. In this case, the engine is operating at 105% of its optimum figure, and the compression ratio has increased to 24:1. The volume of the one unit of air entering the compressor will reduce further than it would at 100% RPM, because the compression ratio is now 24:1. To get through the compressor in the same amount of time it took when it was compressed at a 22:1 ratio, the decreased volume of air will be moving slower. Once again, the changed relationship between the airflow axial velocity and the RPM will change the angle of attack. But this time, with decreased airflow velocity and an increased RPM, it will generate a high angle of attack over the rotor blade. The reduction in axial velocity happens throughout the compressor. The reduction in axial velocity can reach a point where turbulent airflow and a phenomenon called stall may occur. Stall is a partial breakdown of the airflow through the engine, and is a progressive condition, which, if it's not checked, may produce an event called surge. Surge is a total breakdown of the airflow through the engine, which can, in the worst case, cause the airflow through the engine to instantaneously reverse its direction of flow.